Hello, my name is Jasmine Pankratz, and this is my project for IE 4318 Data Mining and Analytics, Predicting Colorectal Cancer Survival with Machine Learning. Background. Colorectal cancer is the third most common cancer and second leading cause of cancer deaths worldwide. Early detection and treatment dramatically improve survival rates. Risk factors include genetics, diet, physical inactivity, obesity, smoking, and alcohol use. The 5-year survival rate depends heavily on the stage of cancer at diagnosis, where there is a 90% survival rate when caught early and less than 15% for late stage metastatic cases. Machine learning is a powerful tool for uncovering patterns in complex data, enabling smarter predictions, automation, and decision-making across a wide range of fields, and has many applications in healthcare, in this case, cancer care. Some of those applications include survival prediction, just estimating short and long-term survival based on patient features, risk stratification, identifying high-risk individuals for early screening or intervention, treatment personalization, predicting which patients benefit most from surgery, chemotherapy, or immunotherapy, recurrence detection, flags patterns that signal likely cancer return, tumor classification, distinguishes benign from malignant or grade tumors using imaging or genomic data. Medical imaging, which assists radiologists in detecting tumors via CT, MRI, and colonoscopy scans, as well as biomarker discovery, which analyzes omics data to find predictive biological indicators. The objective for my project is to predict 5-year survival in colorectal cancer patients using machine learning. The goals include performing exploratory data analysis, pre-processing and transforming data, building and tuning multiple classification models, and evaluating and comparing model performance. The dataset I used contains global clinical and lifestyle data on colorectal cancer patients, which includes demographics, risk factors, and medical history. The dataset contains 167,496 samples with 28 features. The target variable is survival of 5 years. My pre-processing steps include encoding binary yes and no columns to 1 and 0, using one-hot encoding for categorical features, standardizing continuous features, dropping the columns for irrelevant features or columns with high missing values, and then splitting the data into training and testing sets at an 80 to 20% split. An important step in data analytics is data visualization. Here I have the survival count by country. From this graph, we can see that the US has the highest number of 5-year survivors at 15,477. New Zealand has the lowest at 2,003. Here we have the age distribution. Patients range from 30 to 89 years of age. As you can see from the graph, the majority of the patients are 50 years or older. Here we have the sex distribution and cancer stage versus survival. Sex distribution is 60.1% male and 39.9% female. As you can see from figure 4, there are more survivors with localized or regional cancer versus metastatic. Feature selection. To reduce dimensionality and focus the model on the most informative predictors, I applied feature selection using the select k-best technique with the mutual information classification scoring function. Why mutual information? Mutual information measures the dependency between each feature and the target variable. Unlike correlation, it can capture nonlinear relationships, making it well suited for a mix of categorical and continuous variables. Feature selection was performed only on the training data within each fold of the cross-validation pipeline. This avoids data leakage, ensuring that no information from the test set influenced feature selection. I retained the top 15 features with the highest relevance to the target variable. These selected features were used across all models for consistency. By standardizing the feature set across all classifiers, the comparison between models remained fair and unbiased. This ensures that any differences in performance were due to model behavior and not variations in input data. I chose 5 machine learning algorithms that are widely used because of their strong performance, flexibility, and ease of use. Logistic regression for general purpose and interpretability. K-nearest neighbors, which is an instance-based model. Multi-layer perceptron, which is a neural network. Random forest, which is an ensemble method. And XGBoost classifier, which is also an ensemble method. Logistic regression is a supervised machine learning algorithm used for binary classification. Despite the name, it is actually a classification algorithm, not a regression one. There are several steps it takes. First, it creates a linear combination by calculating Z, a weighted sum of input features. It then passes Z through a sigmoid to squeeze the output between 0 and 1. This gives the probability of the positive class, in our case, surviving 5 years. Lastly, we have thresholding, where if the probability is greater than 0.5, then its prediction is the positive class. In other words, will survive. Otherwise, it predicts the negative class or will not survive. Logistic regression has several strengths. It's simple and fast. It works well for linearly separable data. It provides probability scores, not just class labels, and it's easy to interpret where feature weights influence outcomes. Limitations. Logistic regression assumes a linear relationship between features and the log odds of the outcome. So it doesn't handle nonlinear patterns well. It is also sensitive to outliers and multicollinearity. For this model, I ran it under several different regularization parameters, 0.01, 0.1, 1, and 10. K-nearest neighbors is a non-parametric, instance-based machine learning algorithm used for classification and regression. It works by storing the training data. KNN does not build an explicit model. It just memorizes the training data set. It computes the distance between the test point and all training points, typically using Euclidean distance. It then selects the K closest data points or nearest neighbors from the training set, where K is user-defined and equals the number of neighbors to consider. A small k is sensitive to noise, and a large K has a smoother decision boundary. Then lastly, we have voting. For classification, the majority class among the neighbors is predicted. So if 3 out of the 5 nearest neighbors survived, the prediction is yes. In regression problems, the average value of neighbors is returned. Some of its strengths are that it's simple and intuitive. It requires no training time, just memorization, and it naturally handles multi-class problems. Some of its limitations are it has slow prediction time for large data sets. It has to compute distances to all points. It's also sensitive to irrelevant features and feature scales, and performance depends heavily on K and the distance metrics. For my KNN model, I tried several different parameters. For the K value, I used 3, 5, and 7. And for the distance metric, I used 1 and 2, where 1 is Manhattan distance and 2 is Euclidean distance. Multi-layer perceptron is a type of artificial neural network used for classification and regression. MLPs are made up of layers of neurons, an input layer, one or more hidden layers, and an output layer. The input layer receives the features. Inputs are passed to each neuron, which computes a weighted sum of inputs and applies a nonlinear activation function. The output layer produces the final prediction. Then we have training. Through backpropagation, the network calculates how much each weight contributes to the error and adjusts those weights using gradient descent algorithm to reduce the loss. This process repeats over many iterations, gradually tuning the weights so that the model learns which features and patterns are most predictive of survival. The goal is to minimize the loss and improve accuracy on unseen data. Some of its strengths include that it can capture nonlinear relationships that linear models can't. It's highly flexible with numbers of layers and neurons. It's effective when the data set is clean and features are informative. Some of the limitations are that it needs careful hyperparameter tuning. It's prone to overfitting on small data sets, and it requires scaled inputs. I tested my model with various levels of hidden layers, used activation functions sigmoid and ReLU, with the solver as atom and maximum iterations of 1000. Random forest is an ensemble learning algorithm that's used for both classification and regression. It builds many decision trees and combines their outputs to make a final prediction. How it works, it uses a technique called bagging or bootstrap sampling, where it creates multiple random subsets of the training data with replacement, and each subset is used to train a separate decision tree. At each tree split, only a random subset of features is considered versus all of them. This introduces diversity among trees and reduces correlation. After all trees are trained, they each make a prediction. In classification, the model uses a voting system. Whichever class gets the majority vote is the final prediction. For regression, it averages the outputs from all trees. Its strengths are it is robust to overfitting, especially compared to a single decision tree. It handles both numerical and categorical features. It can manage missing or noisy data and even gives us feature importance scores. Some of its limitations are that it can be a bit slower to train and is less interpretable than a single decision tree. The hyperparameters I tested my model on include for criterion, Gini, and entropy, maximum depth, or how deep each tree can grow, 3, 6, and 9, the maximum number of features, and 100 estimators, which is the number of trees in the forest. XGBoost stands for Extreme Gradient Boosting. It is a powerful, fast, and efficient implementation of gradient boosting, an ensemble of models, typically decision trees, in a sequential manner where each new model is trained to correct the errors made by the previous one. The process starts with a weak model or a shallow tree. The model makes predictions and computes the residuals. Then a new tree is trained on those residuals, learning where the previous model went wrong. The predictions from the new tree are added to the overall model. This process is repeated many times, gradually improving accuracy with each iteration. XGBoost has several strengths. It's known for very high accuracy, especially on structured tabular data sets. It includes built-in regularization, which helps prevent overfitting. It is fast and scalable, and it can handle imbalanced data. Some of its limitations are that it requires careful hyperparameter tuning to perform well. It's also less interpretable than simpler models like logistic regression. And if you don't tune it properly, it can still overfit, especially with too many trees or weak regularization. The hyperparameters I tested on my model are 50 and 100 for estimators, maximum depth of 3 or 5, learning rate of 0.01 and zero point 0.1, and subsample 0.8 and 1. Tuning and evaluation methods. To ensure reliable model comparison and prevent overfitting, I used nested cross-validation. I used a threefold inner cross-validation loop to search for the best hyperparameters using Grid Search CV. Then evaluated model performance using a fivefold outer cross-validation loop. This approach ensures the models generalize well and that their performance isn't overly optimistic due to tuning on the same data they're tested on. The primary evaluation metric I used was balanced accuracy. This is especially important for imbalanced datasets where standard accuracy can be misleading. In addition to balanced accuracy, I used several other performance metrics. Accuracy, which is the overall proportion of correct predictions, sensitivity or recall, the ability to correctly identify positive cases, specificity, which is the ability to correctly identify negative cases, precision, which is the proportion of true positives out of all positive predictions, and F1 score, the harmonic mean of precision and recall. I also use the mean, balance, accuracy, and standard deviation across folds to assess overall performance and consistency. To compare models statistically, I used an ANOVA test, which gives an F statistic to assess variation between model performances, and a p-value to test whether the differences were statistically significant. For direct pairwise comparisons between models, t-tests can be used. Results. For the logistic regression model, I use this as a baseline model for comparison. The mean balanced accuracy was 0.50 with a standard deviation of 0, meaning no variation. The recall for the positive class was 1 and for the negative class 0, which means the model only picked positive class. It did not predict any for the negative class. This means that it is not a good fit for the data set, and likely a nonlinear model would work better. Here I have the performance metrics of the nonlinear models that I built. The balance accuracy scores ranged from 0.4981 to 0.5001. The accuracy scores range from 0.5354 to 0.5992. The overall performance of my models was mediocre. Out of all models, the best performing one was XGBoost. The last test I performed was the test. This gave me an F statistic of 0.4838 and a p-value of 0.6982, which failed to reject the null hypothesis, meaning there was no statistically significant difference between the models. Because of this, there was no need to perform the pairwise t-tests. As an afterthought, I decided to check the survival rates by country, mainly out of curiosity. As you can see here, the survival rate is about 60% for all of the countries, which is not a realistic representation of survival rates among various countries. This consistency in the survival rate is likely why none of the models performed well. To conclude, a few key findings. All models achieved approximately 50% balanced accuracy. Despite using a variety of algorithms, including ones like Random Forest and XGBoost, all models performed to chance level. This suggests that the models were unable to find patterns strong enough to meaningfully differentiate between patients who survived and those who did not. Logistic regression failed to predict the minority class. The logistic regression model predicted only the majority class. Yes, likely due to class imbalance. It did not detect any no cases, leading to poor recall and specificity and a balanced accuracy of exactly 0.50. Some of the data analysis insights: weak correlation between predictors and the survival outcome. Feature selection and permutation importance both revealed low predictive power for most features. This implies that even advanced models had little signal to learn from. Survival rate consistency. When the survival rates were grouped by country, the percentages were nearly identical across all regions at about 60%. This further supports the idea that demographic or geographic features did not meaningfully influence outcomes in this dataset. Class imbalance. Approximately 60% of cases were labeled as surviving 5 years. This imbalance caused some models to favor the majority class, reducing performance on the minority class and skewing overall accuracy. This leads us to the conclusion. Data lacked strong predictive signal. The dataset did not contain features that meaningfully separated survivors from non-survivors, limiting the model's ability to make meaningful predictions regardless of complexity. Feature quality was the main bottleneck, not model complexity. Even powerful models like XGBoost and MLP perform no better than simpler models. This indicates that adding more complex algorithms won't improve results unless better or more informative features are introduced. And here I have my references. Thank you.